Okay, revision questions. So we just solved a bunch of proof questions. So I'm mostly here going to be focusing on the previous ideas, but there might be a question or two that have to do with trying to prove something. So if we go all the way back, we can remember that we have truth tables. So we practice that. Like, how can you actually make a truth table? And the more important thing is, what can you conclude about these? What's your conclusion about truth tables? Like, is this table satisfiable? Is it a tautology? Are two tables equivalent because they have the same truth value on each assignment? Like for assignment 1, true, true. For assignment 5, false, false. Are they equivalent? And so on. And remember the operator and precedence, because depending on these guys, the whole formula becomes different. Just like we saw in the x less than z and z less than y, depending on like how you read it, how you understand it, the whole meaning changes. I'm not gonna do this. You can do it on your own. Again, with the translation, you're given English proposition, you're given English sentences, you want to change them into propositions or formula using proposition. PQR are these stuff. I probably should have mentioned, I'm not going to add the pause button that we usually have because there's a lot of questions. So if you're trying to solve this while watching the video, you can just keep pausing. Leave your finger on the pause button. Okay, so you get an A in this class, but you do not do every exercise in the book. R and not Q. Getting an A on the final and doing every exercise in this book is sufficient for getting an A in this class. Remember the sufficient and what's the other thing? Sufficient and I'll try to remember it. It slipped my mind. So usually when you have P implies Q, one is sufficient for the other and the other thing that I won't get now. So getting an A on the final and doing every exercise is sufficient for getting an A in the class. The other way around. You're given the proposition, you now want to, or the formula, you now want to change it into English. So this is this, and this is this. Again, if the sentences don't make sense English-wise, it doesn't matter. You're just translating. Necessary. Necessary. So yeah. Getting an A on the final and doing every exercise in this book is sufficient for getting an A. And the other way around, it's necessary. So getting an A is necessary for blah, blah, blah. So that's the other thing. For each of the following, determine if it's an inclusive or exclusive. The school is closed if it is a holiday or a Sunday. It's inclusive. If it's both a holiday and a Sunday, you're definitely not going to go to school. The two lines intersect at a point or are parallel. So yeah, those are parallel. Or this. There's no way both can happen at the same time, so it's exclusive. And in recitation 1 or in practice set 1, I may have gotten confused and there was something called intended. Like the question was saying prove if it's an inclusive core or exclusive or intended. Intended just meant was just an English word. Like they were saying is exclusive or inclusive intended. Show the stuff. Now that's what I meant by the proofs from the first part of this course. Like here, you're actually trying to prove if this is equivalent to this. And trying to prove if you have this, you get this. For the equivalence, there's lots of ways to do it. You could start from one side and try to reach the other. Like if I start from the left-hand side, so left-hand side, and I say it's equivalent to something, which is equivalent to something, and eventually you reach the right-hand side. Or vice versa, right-hand side, you reach the left-hand side, or move with both of them at the same time. So left-hand side, right-hand side. You say equivalent with a question mark, like you're asking, are they equivalent? And eventually you reach a common place in which they are. Remember the important thing, which is alpha implies beta. It's equivalent to not alpha or beta. That's, if you don't know this, you probably won't be able to solve a lot of this, because we're saying do not use truth tables. Okay, so they should be simple enough. Okay, so for the other one, for the first one, you can use what we said. For the other one with the implication, again, you can try to use the alpha implies beta. So not alpha or beta. For the big one, which is this big alpha and this big beta, and for the smaller implications. So this, and this. And since we're trying to prove that it's valid, it means we want to reach true. And eventually, after you do this, you hopefully want to reach true or something. So you get true. Or you have to prove that, for example, P or not P, and Q or not Q, and so on. Like you're either going to prove true or something big, or if you're constrained by ands, you have to shift it in a way where you get P or not P, so that's true. Q or not Q, so that's true. But trues with ands is just going to give you true. So do that and use the forms if something's not clear. Use quantifiers, predicates, with more than one variable to express these statements. Another way of translating, but now we're not just using propositions, we're using predicates. There is a student in this class who can speak Hindi. So you have to break it down into predicates. So for example, h of xy, x speaks language y. So you have to specify that x is a student, y is a person. You have to ask yourself, what's my domain? Like, do I have to specify that if this student is in my class? You do if we're working with all people. Let Sxy mean person X can speak language Y. Our predicate is there exists X, S of X Hindi. So here they're probably assuming that X is a student. There is a student who has taken every course offered by one of the departments in the school. T of xy mean that person X has taken course Y, and O of yz means course Y is offered by department Z. There is a student who has taken every course offered by one of the departments in the school. There exists X, the student. There exists Z, the department. For every Y, if this department offers this course, then that means the student has taken it. Again, your student X, the department Z. For every Y, OYZ, is this course given by this department? Then this student has taken this course. Some student in this class grew up in the same town as exactly one other student in this class. Some student in this class, there exists, has grown up with exactly one other student. So again, the keywords, some, which means there exist, exactly one, which means you need to take care of that. Let g of xy mean that persons x and y grew up in the same town. So here we're kind of like taking a shortcut. We're not making a predicate that says, for example, txy. We're not saying x lives in town y. It's sort of a shortcut. X and y grew up in the same town. It's okay to take shortcuts if it's reasonable. Then our predicate is there exists x, there exists y. X is different than y, and gxy. So there's a person, and there's another person. They're not the same person, and they live together in the same town. So we took care of everything except the exactly one. And for every z, if x grew up with z, then that means either x is y or x is z. So if there is another person that x grew up with, then either that person is also y or it's himself, like you grew up with your own self, your own consciousness. Okay. Rules of inference. Again, it's one of those ideas where it's 3 points if you practice hard enough on these sort of exercises. So construct an argument using rules of inference to show that all the stuff you conclude that it trained. So you have a bunch of premises, imply the conclusion it trained. So these are your different sentences. You are given these propositions. So in this exercise, step 1 is going to be translating all of these sentences into actual premises that we're used to work on. Like P implies R, not S and Q, all that stuff. Step 1, translate the sentences into these stuff so that we can actually do the rules of inference. So you can pause here and try to do that. Here is what you should get. If this is not what you got, you can try to pause and actually solve it for this. Let's see what happens. We want to conclude R from this stuff. Let me actually take a quick look and see if we can kind of draw a map. So we want to conclude R. The only place where we can find R is in this big thing. So to get this, okay. S and T, not T. Okay. So we can kind of see the map. Like there's only 3 premises. Like obviously you have the not T and you have this. So definitely you're gonna get that not S is a premise, and then you go from there. Because if not T is true, then T is false. S can't be true. S has to be then false. Because true implies false is false, and the premises are all true. So again, don't waste time. If this was an exam, just write and see what happens. Step, not T, S implies T, like we said. So your step, your reason, your hypotheses, or your premise, or your rule, whatever. We get not T, modus tollens, using steps 1 and 2. So again, our hypotheses, what can we do here? Well, we have to do something with this and this. Probably gonna end it with I. Let's see what happens. Ah, that's even better. Okay. So to get that S and I think this is I. To get that S and I is false, you need not S and I. To get that, you need not S or not I. You already have not S, so just OR it with not I. Addition, using step 3. Since not S is false, if you OR it with anything, it's also going to be, sorry, if not, since not S is true, if you OR it with anything, it's also going to be true. De Morgan's, so now we have this and this. So this is false, just like we did with S implies T. That means this part has to be also false. Right? So this has to be false. So the not of it is going to be true. De Morgan's, R and F, simplification, you get R. So that's it. We concluded R. Trying to think if there was any step here that was kind of hard. I guess this was the hardest step, maybe. Like how, like okay, you might have got that, okay, this has to be false, but how can I get this OR idea? Well, it wasn't the first time we saw it. So add it to your arsenal of stuff you can do. Sorry, Samer, which question did you mean? I didn't read that. Was it this one? I'm gonna post the slides right away. Like once I finish this recitation, I'm gonna upload the slides so you don't have to write it. You can then solve it on your own, okay? I'm just doing this quickly in case you need a reference for the explanation. And we're down to our last question. This thing we didn't give it a lot of justice in the recitation, even though we did go over it in the practice exercises, which is the whole EI, UI, and all that stuff. Existential instantiation, universal instantiation, and generalization, and all that stuff. It's not the only way to solve this, but this is what we're gonna do. Let P and Q be two predicates. Prove that there exists X is equivalent to this. Again, before you dive in and try to solve it, try to translate, see what's happening. We're saying that there exists an X that makes P or X or Q of X true. So these are the same X. Is it equivalent to saying you have some X that makes this true and some different X that makes this true? It is, since they're saying prove it. For the implication direction, assume it. Okay, if you want to prove equivalence, you go in this direction, you prove it, and then you go in the other direction and you prove it. So you assume that this is true, and now you want to reach the other side. There exists X, P of X, or Q of X. It's your assumption, hypothesis, premise, whatever. Existential specification, or we're used to saying instantiation. We're just giving an example. So the same X, Px, or Q of X, we just said that let that X be A. So P of A or Q of A. Now, for the first one, generalization, existential generalization, there exists X, P of X. Then for the second one, there exists X, Q of X. And again, these are different X's. It would have been the same if you said here there exists Y, Q of Y. And for the first one, there exists X, P of X. It's the same thing, But since they wanted x by x, that's what we did. They're different x's even if they look the same on the right side. On the left side, it's the same x. Okay. The other way around, you assume the right-hand side and you want to reach the left-hand side. So this is your assumption. The first one, P of A. Then the second one is actually Q of B. So the existential specification, you can't here assume that they're the same x, like we said before. So P of A or Q of B. But since we know that this is, one of these has to be true, or it could be false, we just add it for the other one. Okay, so P of A or Q of B, you can just now add or P of B or Q of A. Why? Because remember, you're assuming that this is true. It's given, it's law. So step 3 is going to be true. True or anything is true, so you simply add or P of B or Q of A. Associativity and commutativity. You put the A with the A and the B with the B. Now we go back with the generalization. There exists X that makes this true, or there exists a different X that makes this true. A or A is equivalent to A. This completes the proof. There's a note that be very careful with step 3 of the going backwards. We have to use different symbols A and B because they are specified from 2 different existential quantifiers. Basically saying this X is different than this X, so you have to use different constants. Okay. For all of these, there were existential. For every, it would have been generalization. Okay. So that's it for the questions. I'm gonna upload the slides right now, and I'll see when I can upload the recordings. If anybody's still here, do you have any questions? I went fast over the revision because I'm assuming nobody's here. This is for you to solve on your own, and then you can check the recording if there's something you didn't understand. Okay, you're welcome. Okay, good. Okay, I'm gonna end this meeting in a couple of minutes. If anybody has a question, let me know.